Okay, our lesson in integration today will be on finding the area between curves. Area between curves as an application for integrals. We studied before two concepts, which were the net area and the total area. Yes, the net area and the total area. Both of these were the area between the function and the x-axis. Both were between the function and the x-axis. We are talking about this area. When we are talking about the net area, we just take each of these areas with its sign. But when we are talking about the total area, what do we do here? We make any negative area, we make it as positive. That's why we told that the total area is just the integral of absolute the function, which makes all the function above the x-axis. Okay, so we learned before the difference between the net area and the total area, and both of these areas are talking about the area between the curve and the x-axis. Okay, now we need to learn today how to find the area between two curves. If I give you some function f of x, f1 of x, and another function f2 of x, and I want to find in some interval the area between these two curves. The area between these two curves. How would I find this area? If I have understood the concepts on which the integral is based on, we can find here the area between curves. What was the area? What was the concept of the integration based on? It was based on, if we have this function and we are talking about the area of this strip. The area of this strip, which had length dx and the other length was f, or the other height was f of x. So the area of this strip is f of x multiplied by dx. Then we sum these little small areas. Okay, this sum is just a capital S, but we just stretching it like this, so we had the sign of the integral like this, and this is we make it from a to b. So this symbol of integration is just an s but stretched. This is the s of sum. Okay, it is just summing these infinitesimal areas. Okay, now we will just use the same idea here. I can say that this area, we can find the area of this strip. The length of this strip, or it will be dx. And the height, what would be the height here? It is, we know that this length is f of x. All of this is all f1 of x, and that other one is f2 of x from this point to the x-axis. So if I want to find this black area of the strip, that would be that length. If I need the length of this strip, what would it be? It would just be the above curve minus the below curve. So it will be f1 of x minus f2 of x. So this is the height of the strip, and I multiply it by its base, which is dx. Then I integrate from the starting to the end, which is a to b. So now this is just the law that we will use to find the area between two curves. Okay, this is the area between two curves, which is, we can call it y1, y1 or y1, the above integration from a to b, y above minus y below, dx. And when I say dx, it means that we must express both these functions in terms of x. Okay, when I tell you y minus y, I mean here, but y above, it is y, it is equal f of x, some f of x. I should determine if it is f1 or f2 from the graph of the function by knowing what function is the above function, what is the below function. Okay, so this is the first law. The second law is finding the area between two curves, but sometimes it is better to look at it horizontally, to look at the strip horizontally instead of vertically. This strip was a vertical strip. This is a vertical strip. Sometimes I would have a curve like this and another curve like this. Now notice here that these functions, these are called curves or maybe relations. Why it is not a function? Do you remember? We took this in math 1. Why this is not considered as a function? A function would have some conditions to be a function. One of it is that the vertical line test. Do you remember? The vertical line test, we shouldn't have any vertical line test. We shouldn't have 2 points in any vertical line. Okay? So if we have some vertical line which have some more than one intersection, it is just considered as, it is not a function for us. It is called a relation. Just like a circle, a complete circle, it is not considered as a function. But we can consider it as two functions. This is a function and another one is another function, because the function should comply the condition that the condition of the vertical line test. Okay, now if you want, sometimes we would have some functions that would be easier if we look at it with horizontal strip instead of a vertical strip. Sometimes it is just very obvious what are the limits in the y-axis, like this, and we can just variate the y from A to B to find this area. If this problem, if I like to make it in as a vertical line test, with a vertical line instead of a horizontal line, it will be a very cumbersome problem. I will just need to find how to make this strip and how to make another one. I will just need to break my integrals, to break the area into too many separate areas. So it is not convenient here to make it with a vertical strip. It is more convenient here to work with a horizontal strip. Okay, now what would be the law for the area here? Just if we had understood the basic concept, which is, now what is the base of this strip? What would the length of its base? It would be, it is now dy. Yes, it is now dy multiplied by the height of this strip. It will be, now this is a relation. It is a relation between x and y. How would we express it? We would express it now as x1 of y and x2 of y. We are integrating with respect to y, so we need the first function to be x of y and the other function to be x of y. Which is first? We take here the right, so x right and this is x left. Okay, the right function minus the left function. Why? Because in the right side we have always the greater value. For any two numbers, the one at the right is always greater than the one on the left. So for the area to be positive, we just need to make it as the right curve minus the left curve. Also in the vertical strip, we just made it the above function minus the lower function. Why? Because the above function has a larger value than the lower value, so we need this to be a positive value after all. Okay, now this is the law for using a horizontal strip. X right minus x left, or the function on the right minus the function on the left, dy. Okay, before starting seeing some problems, we need to revise some known curves. For example, we need to know how to graph a straight line. As you will see here in area problems, we need to graph the problem. So some curves, we need to graph them, and we will just give a brief revise for the or a brief revision for the for some known curves, like the straight line. A straight line is expressed as y equals mx plus c. How to graph a straight line? We just choose x equals 0 and see what will be y, and then choose y equals 0. We just choose 2 points and connect between them like this. These 2 points, for example, may be one to be here and the other will be here. That will be x equals, then we write the point x1 y1, and the other point will be x2 y2, and we just connect between these two points. Okay, this is how to graph a straight line. If we had y equals 3, how can we graph a line that is y equals 3? Yes, it is one that is parallel to the x-axis. Y equals 3 is parallel to x-axis. And what is x equals 2? That will be a vertical line parallel to the y-axis. So this is x equals 2. Okay, this is the straight line. Also, we need to remember, and we took that in math 1, we need to remember the parabola. A parabola is something like this, and this is called x equals y squared, or some c y squared. X equals c y squared. If this c was negative, it will just be like this. Okay, now it is looking at a horizontal, it is just in horizontal direction. The direction which it is looking at is just the direction of the variable of the first degree. Okay, it is just the degree of the variable. So if we had, for example, y is equal to cx squared, it will be directed in a y direction. So it will be like this. This is the variable with the first degree, y power 1. So it will be looking in a vertical direction. And if this constant was negative, it will be looking at the negative y direction. Okay, so this is a parabola. And you have learned to graph a parabola by, if I had something like this, y squared minus 2y plus x equals 1. How would I graph this parabola? This is a parabola. One of the variables is first degree and the other is a second degree. So I've known here that it is a parabola. If one of the variables is a first degree and the other is a second degree, so this in analytical geometry, this is known as a parabola. Okay, how would I graph it? What do I do for the second degree terms? I make complete square. Yes, complete square. Y minus 1 all squared minus 1 plus x equals 1, and that will be y minus 1 all squared plus x equals 2. I need the first degree term to be in a side, and the other will be like this. So this will be y minus 1 all squared in negative. And also you have 2. I will just write 2. If you look at these expressions, they don't have a constant. So just take the constant with the x. We make it like this, x minus 2. And put the x in a bracket, the linear part of the x in a bracket, and the linear part of y in a bracket like this. So this is much like which of these four? First, the x has the first degree, so it is horizontal. And we have here a negative sign, so it is looking at the negative horizontal direction. Okay, but we have here, yes, we have here the vertex. We need to determine the vertex. I'm just deciding here the direction. I've known that the direction will be in a negative horizontal direction, but I first need to know the vertex of the parabola, which is this point. Where would it be? What would be the vertex of this parabola? 2, which makes the bracket of x to be 0, is x equals 2. And what makes the bracket of y to be 0? 1. So this will be 2 and 1. So this point 2 and 1, this is exactly the vertex of our parabola. If I need to graph this parabola, I just make some illusionary axes like this, and I draw the parabola looking at the negative horizontal direction with this point 2 and 1 as the vertex of our parabola. Okay, this is one way to find the graph of the parabola. Another way is to see when does it intersect with the x-axis or the y-axis. Okay, another way to graph this function, y squared minus 2y plus x equals 1. Another way to graph this function is to put x in some side and the other variable, all the other terms in the other side. So it will be, or I would take these to the other side, it will be 1 minus y squared plus 2y. And I just check when this side would be 0. I would check when this side would be 0. So when I check this, it will be, I check it y 1 plus 2y minus y squared. When would it be 0? I solve this equation. Okay, this equation may give me two numbers. These two numbers will be plotted in the y-axis. It will give me y and y equals and y equals, two y's. So these two y's are plotted on the y-axis. Okay, and just now I need to know if it is looking in the negative direction or in the positive direction. How would I know that? By looking at the sign of x and the sign of the second degree. If they are with the same signs, it will be looking positive. If they have different signs, it will be looking in the negative side. Okay, so this graph will be something like this. Okay, sometimes as we in integration or in finding the area, we already will need to find these points. So maybe this method would be more convenient or maybe faster than completing squared and finding the vertex and graphing this. Then we'll find these 2 points. We will need these 2 points in our steps in finding the area. Okay. So we have learned how to graph a line, how to graph a parabola, how to graph a circle. If we had a circle like this, if I had x squared plus y squared equals r squared. This is a circle with a center, is the origin, and has a radius r. If I had x squared plus y squared equals 16. So this circle will be in the origin, and what is this point? 4. Yes, the radius here is equal to 4. If it was like this, x minus 2 squared plus y plus 1 all squared equals to 9. This circle has, where will be the center here? It will be 2 and minus 1, and the radius will be 3. So this circle will be 2 minus 1, and the radius is 3. So this is the this is our circle. Okay. If I give you something like this, if I say y is equal to root 4 minus x squared, this is considered a circle also, but it is not a whole circle. First, why it is a circle? Why it is part of a circle? If I square both sides, it will be y squared equals 4 minus x squared. And if I take x squared to the other side, it will be x squared plus y squared equals 4. So this is a circle. But why am I telling you that it is not a whole circle? Yes, I'm saying here that y is a root, and the root is always positive. A root is always positive. So I am saying here, we can deduce here from this expression that y is positive. I'm taking the part of the circle for which y is positive. So I'm taking only this part. This will be graphed only the above semicircle, or the positive semicircle. If the circle was expressed like this, x is equal to 9 minus y squared, what would this expression denote to? It will be a half circle too. Take this circle with the radius 3, but which part of the circle would it be? Yes, it will be a right side only. The right side only. Why? Because I'm telling here that x is positive, so I'm talking about the positive side only. The positive side only, or the right side only of the circle. Okay? Some other graphs, like the power functions, we have known that before, from y is equal to 1 over x. 1 over x is graphed like this. We have to know these graphs. 1 over x is graphed something like this. If I had 1 over x squared, this is much like 1 over x all squared. So any negative, I just need to square this function. What does squaring do to the negative? It makes it positive. Okay? So any negative will be positive. So the graph of 1 over x squared is much like the graph of 1 over x. But it is much slimmer, and any negative is positive. It just gets slimmer like this. If I graph both on the same graph, it will be something like this. Slimmer. Why? Because squaring makes it quicker for the difference. For any change in the function would be quicker. Okay? And so on. If I had 1 over x cubed, how would I graph this function? It would be the same as this, but slimmer. Would I change the negative to be positive? No. It will just be like this. Okay? So this is a power function, but for negative values of the power. What if I had a power function but for positive values like this, y is equal to x cubed? Do you know the graph of y equals x cubed? It is just like this. Y is equal to x squared or x power 4 or x power 6. It will just be like this. But this is x squared. This is x. This is x power 4. It just gets compressed, and this will be x power 6 and so on. Okay, so for even powers the graph of the function is like this. For odd powers x power 5, x power 7 and so on, it will be just the same graph as this. So it will be x power 5 will be just like this, and so on, x power 7 and so on. That will be x power 7 and so on. This is x power 3. Okay, also you need taking the absolute of a function. What is meant by taking an absolute of a function? For example, if I need to graph the function absolute 1 over x or something like this, this is just the absolute of a function. What does the absolute do for a function? This is the graph of 1 over x. This is the graph of 1 over x, like this. Yes, an absolute will just make the negative to be positive, so it will be something like this. But it will not change, it won't be slimmer or something like that, it will just be as it is, but just changing the negative to be positive. So this is the graph of 1 over absolute x. Also, I need to know the graph of absolute x, or any or something like that, x minus 2, for example. I just graph the function inside the absolute. Then what would I do for this straight? This is a straight line. I graph it like this, and it has a positive slope, so it would be like this. Positive slope, it would be like this. Then I make all the negative to be positive, so the graph of the function will be like this. This is absolute x minus 2. I just graphed the function inside the absolute, and any negative I took it above the x-axis. Now let's see some problems on finding the area between two curves. Find area between 4x minus x squared and x-axis. So this is a problem. Maybe you can consider it as a net area, or as a total area, because it is with the x-axis. First, let's graph the function. This area, when I'm finding only any of these areas, we need the areas to be positive. I can't have here a result with a negative value in all this lesson. So what is this area with the x-axis? What would be considered as a net area or a total area? Yes, this is a total area. A total area which is considered always positive. Okay, now let's graph this function. One method to graph this function is to make completing square and finding the vertex and then graphing the parabola. I've known here that it is a parabola. Y from y it is raised to the power 1 and a second degree for the x squared. 1 is the first degree and the other variable is a second degree. So I've known that it is a parabola. A horizontal parabola or a vertical parabola? It is a vertical parabola. Why? Because the first degree is a y. So since it is a y, so it is a vertical parabola. Now we need to graph it. I've taught you how to graph this. I need to find when would this side be 0. 4x minus x squared equal to 0. I take a common factor, x minus 4 or 4 minus x is equal to 0. So this would give me 2 points, x equals 0 and x equals 4. So I have here 2 points of intersection, x equals 0 and x equals 4. Now I need to determine, would it be looking downwards or looking upwards? It would be looking upwards. Why? Yes, downwards. Why downwards? Because the sign of y is different from the sign of x squared. Since they are different, now we have it is looking downwards. So the graph of the parabola is like this. Now the problem is requiring the area between this graph and the x-axis. So these are the two curves that I'm looking for the area between them. This is the first curve, which is the x-axis. The other curve is this. I should determine the region that I'm looking for its area. What is the region here? The region should be closed. This is considered to be between the x-axis and the parabola, but I cannot consider it here to be the considered area. Why? Because this is an open area. Okay, I'm just looking for a closed area between these curves. Which of the what would be a suitable region here? It would be this region. Okay, so this is the area that I'm looking for its value. Now I need to express it with the area and with the integral. What is better here, to make it with a horizontal strip or a vertical strip? Actually, you can make it both ways. Let's make it with the easier procedure. I will just take a vertical strip. Okay, that will be the above function. It will be dx, and the integral will be from the above function to the lower function, a function of x minus a function of x. This should be expressed as y equals function of x, so 4x minus x squared. If I give you the function as expressed like this, y minus 4x equals minus x squared, before using it in the integration, I should put the y in a side and all the x's in the other side. Before using it, I should write it like this. This is y of x minus y of x. I should put here a function of x minus a function of x. Okay, the above function is minus x squared plus 4x. This is the above function. What is the below function? It is 0, yes. Now this strip, to cover this area, I would take it or slide it from x from what to what? Or from where to where to? From x equals 0 to x equals 4. Yes, these are the points of intersection. And as you can see here, I needed to find these points of intersection. So we just make this integral. Okay. Let's see an example here. Find the area between x equals 1, y equals x, and y equals 2x. let's graph these functions. X equals 1 is considered as a straight line. Yes, this is a straight line, x equals 1. Y equals x. This is also a straight line, and it passes through the origin. Any straight line without a constant, it's considered to be passing through the origin. So it would be like this with an angle pi over 4. So this is y equals x. And another straight line, y is equal to 2x. This is another straight line, but with a larger slope. A larger slope will be like this. This is y equals to x. It also passes through the origin. Now, what area of these, or what is the region here? What is the considered region here? It is that bounded by these black curves, or these black lines. What would be the region here? It would be just this part. Okay? Now I will solve this problem in two methods. First, by a vertical strip. With a vertical strip, I just make the integral from, or just make it like this, the above curve minus the below curve. For the vertical strip, it will be dx. The base will be dx. So I need here functions of x. Any curve, I would express it y as a function of x. All the x's in one side. Okay? What would be the above curve? It would be 2x. Minus the below curve, it will be x. And I would like to slide this strip from x equals to x equals. I slide it from x equals 0 from this point to cover the area. I would like to slide it to x equals 1. So the area can be found only by this integral. What if I like to find the area using a horizontal strip? What if I like to find it as a horizontal strip? If I like to find it as a horizontal strip, I will just graph it again. But just make it wider to see the effects. This is y equals x, and this is y equals 2x, and this is our region. Okay? Now I want to cover it with a strip. This is a strip, but this is another strip. I need to cover all the region. I need to cover the whole region. But when I define some strip here, I just say that this area would be separated like this. And for that above region or above part, the strip here is different from that. How did I know that this strip is different from the other one? A strip is different when we change any of the sides of the strip. Any change in the strips, in the sides or the limits of the strip, if you make any change, even if you swap them, that would be considered a new strip. Okay? So now I have two parts. But I need first to find Now I am taking it with a horizontal strip, so it would be dy. I will take 1 first and make the integral. I needed to make it from y equals to y equals, so I need to know this y, what it is equal to. This x is 1, this x is 1, and it is intersecting with y equals x, so it is obvious that y will be also 1. So this strip slides from y equals 0 to y equals 1. I just need to now to state the length of the strip. What is the length of the strip here? It is the right curve minus the left curve. But remember, I need to express any of these curves as a function of y. So this curve, I just take it like, I express it like this. X is equal to y. And I will express the other straight line, instead of saying y is equal to 2x, I express it as x equals to y over 2. Yes. So now for this step, for this strip, the right curve will be x, will be y, and the left curve will be y over 2. This is the first part. For the second part, the second integral, the strip slides from y equals 1 until y is equal to this point of intersection. So I need to know this point of intersection will intersect in which y. So I intersect y is equal to 2x with x equals 1. This is the point of intersection between this straight line and this straight line. So I intersect between both. That means that y will be, no, not 0, it will be 2. I just substitute here x equals 2. When I find the intersection, it means that these both two are made simultaneous. The simultaneous equations. So I just substitute x equals 1, it will give me y equals 2. To this point is 2. So I slide from y equals 1 to y equals 2, 4, and this is dy. Now I just need to express the strip, the length of the strip, the right curve minus the left curve. What is the right curve here? X equals 1, so it is just 1. This is x equals 1, so I just take this side minus the left curve, which is y over 2. Yes. So now what would be the area? The total area will be 1, the result of the first integral, plus the result of the second one. Okay? Now for the previous problem, if we would solve it by a vertical strip, it would be we would face a problem here, because we have here the curve on the right is just the same curve on the left. Actually it is not the same curve, but I need to express this as a curve x equals to some function of y. How would I express this? I know that y is equal to 4x minus x squared. I need to express that x is equal to something, to some function of y. Do you know how to express it as a function of y? I'm just looking at this as an equation in x. I can consider it like this: x squared minus 4x plus y is equal to 0. And consider y as if it is a constant. Then solve this quadratic equation. So it would be x is equal to 4 plus or minus root 4, which is b minus 4, no, b squared, which is 16 minus 4ac, it will be 4 all over 2, and that would be 4 plus or minus root 12 all over 2. No, this is y, that would be y, 4y, 16 minus 4y. Minus 4y. So this is x. If you notice here that we have here two expressions for x, one with the positive sign and the other with the negative. These are just the two sides of the parabola. So this side, this right side, can be expressed as x is equal to 4 plus root 16 minus 4y over 2, and the other side is with the negative x 4 minus root 16 minus 4y all over 2. And you can notice here that if I make the difference between these two curves, I can get the area, but it is obvious here that this path for solving the integral is better than this one, which contains roots and solving for x. All these steps are considered by just changing the direction of the strip. It made a difference in the easiness of the problem. Let's see another problem. If I have here, find the area between x squared equals to 2 minus y, y equals x, and y axis in first quadrant. Find the area between. Now we have a parabola. We have a straight line and the y-axis. So I just make a graph for these curves. It's better to make the graph with two colors to differentiate or to make a difference between the boundaries of the curves and the axes. So you don't consider the axis as one of the bounding curves. Okay, now he's telling me that I have x squared equals 2 minus y. I may look at it as y is equal to x squared, it would be y 2 minus x squared. I just made the first degree term alone in a side and all the other in the other side. Then I solve it in x. 2 minus x squared, I see when it is equal to 0, which will give me x is equal to plus or minus root 2. So x is equal plus or minus root 2. Now this parabola, would it be looking upwards or downwards? It will be downwards because we have here different signs for y and x. So this will be like this. Okay, I will draw all these in black to differentiate it from the blue axes. Now I have here also y is equal to x, which is like this. Y is equal to x, and this one is x squared equal to, or I'll make it y is equal to y equals 2 minus x squared. Okay, these are two curves. Now I need this also. This is one of the bounding curves, which is the y-axis, which is this. If I didn't tell you an additional condition here, or which is in the first sequence, I would consider two regions. This region is acceptable, and also this region is acceptable. It is a region bounded by these black curves. Now remember, I don't consider the x-axis as a bounding curve. That's why it is better to see the curves in a color and the axes in other color, so we don't mix between the bounding curves and the axes. Okay, sometimes students mix between them and consider, for example, consider this as an axis and take, for example, this area only. For example, I'm just giving an example of some known mistake. Okay, so it's better, it is always better to draw or to graph the axes in a color and the curves or the bounding curves in another color. Okay, now I told you, now we have this region, it is acceptable, and the other region is also acceptable. But he is giving me another condition which is in the first quadrant. If I had more than a region that is acceptable, I just by default take the one that is in the first quadrant. Okay, so if I had, for example, if I give you in the exam this problem but without this condition, we just make it by default. If I had two acceptable regions, I decide which one of them. I just by default we take the one in the first quadrant. Okay, so now our region is this one. It is obvious here that it is, as he is telling me, that it is in the first quadrant. Okay, now I need to find the area. What would be better, if I take it as a horizontal strip or a vertical strip? If I took it as a horizontal strip, how many strips would I need? 2. I would need to separate the area like this, because I have here a strip and I have here another strip. Each strip has different limits. But if I made it with a horizontal with a vertical strip, what would be the result? Yes, I will just need only one strip to cover the whole area. If you slide this strip and cover the region with it, you will find that the limits of the strip doesn't change for the whole region. The bounds or the limits of the strip won't change. Any change in the limits of the strip, I will need to define a new strip for it, and so I would need a new region and so on. Okay, so I can see here that it is that the vertical strip is better, so I would make it as my choice here. So I choose here a vertical strip. So what would be the area? The area would be integration of, that would be the x. The base here is the x. What is the length of that strip? The length of the strip will be the above curve minus the negative curve, and I need to express all the curves as y equal to a function of x. All the curves, I need to express them like this: y as a function of x. For this one, it is already expressed here, so I would write it 2 minus x squared. This is the above curve. What is the lower curve? It will be just x. Now I need to slide this area, this strip, from x equals 0 to which x? Oh, now I need to find this point of intersection. I need to find this point of intersection. This is the intersection between this curve and this curve. So I just intersect between them, which will give me this equation: x is equal to 2 minus x squared. which gives me the equation x squared plus x minus 2 is equal to 0. If I solve it, I find it that x 2 1 minus plus or plus minus, so it will be x is equal to minus 2 and x equals to 1, and these are exactly the 2 points. This is equal x equal to 1 and x is equal to minus 2, which shows this intersection between the same two curves, which will give me this point, but I don't need this point as I'm taking only this region, only the region on the right of the y-axis. So that will be x is equal to 0, 2x is equal to 1, which is this point of intersection. Okay, so this is the expression for the area in this problem. In this example is find the area between y is equal to 4x minus x squared and x and y is equal to x squared minus 2x. I will just give it in the interval 0 to 4. Let's graph these two parabolas. For the first one, it is expressed the first degree is on one side and all the other terms on the other side, so I intersect it with the axis, which I make this equal to 0. 4x minus x squared equal to 0. It will give me x equals 0 and x equals 4. X equals 0 is here and x equals 4 is here. So this parabola would be looking upwards or downwards. It will be looking downwards like this. Now for this parabola, I can make the same steps here. X squared minus 2x is equal to 0. It will give me x equals 0 and x equals 2. And this is the other 2 points. I just make the curves in black to differentiate between the bounding curves and the axes. Now the other parabola is intersecting in the 2 points 0 and 2. Now this is looking, yes, it is looking upwards now, because we have here the same signs for y and x squared. So it will be something like this. Okay. Now if he had told me that to find only the area between these two curves, if the problem was only limited to this information, I would find this area in this case. I would find this area, this curve. Okay, let's make the problem into also find, then find area between the two curves from 0 to 4. Okay, so this is the first problem and this is the second. For this problem we just need what is the region here? It is this blue region. This blue region, would I consider the axes to be separating them? No, it is not. The axes here are not part of the region. I'm just looking at this region here. Okay? Now what would be the area for the first requirement? It will be integration of what strip is more convenient here, a horizontal strip or a vertical strip? If I had a horizontal strip, the horizontal strip will change, and I would separate the area in these two parts. So that's not, yes, a better choice is to make it a vertical strip like this. Now remember, the strip has one end on a curve and the other end on the other curve. It is not related to the axes. Why? Because some students make it like this. They make a strip like this and maybe some other strip like this. No, I don't consider the problem in this way. When I define a strip, I defined it between two curves, two bounding curves. If the x-axis was one of the bounding curves, I would put the strip ending with, on it. But now it is not the case here. Okay, so the integral will be dx. Now I would like to write the form of the integral: the above curve minus the x curve, and each of the curves should be written in the form y is equal to some x. Yes, it is ready here, so I'm taking here y is equal to, this will be 4x minus, the above curve is 4x minus x squared. That is the above curve. What is the lower curve? It is the x squared minus 2x. Now I should slide the strip from x equals 0 to 2. No, 2 was the intersection between the curve and the x-axis. I need to slide it until this point, which is the point of intersection. So I need to find the point of intersection between these two curves. What is the point? How to find the point of intersection? I need to intersect these two curves. So I just write 4x minus x squared equals to x squared minus 2x and solve this equation. Okay, it will give me 2x squared minus 6x is equal to 0. Which is x squared minus 3x is equal to 0. When I take x as a common factor, x minus 3 equals to 0. It will give me x equals 0 and x equals 3. So this point of intersection is at x equals 3. This point is at x equals 3, and the point of intersection, and this point with the x-axis, which was at 2. So I slide it from x equals 0 to x equals 3 and find this integral. Okay? Now for the other part of the problem, which he extended the problem to be find the area between the two curves, but from 0 to 4. But from 0 to 4. Now I will graph the function again to look at the difference carefully between the two problems. I first had this curve at 2, no, this was at 4, and the other one was, I will make it in black. At 4, and the other one was at 2, and it was like this, and the point of intersection was at 3. Now he's telling me to find the area between both curves from the or in the interval from 0 to 4. When he states some interval, I must take it from the first limit to the second limit, which is from 0 to 4, like this. Now what would be the region? I'll just complete this to be something like this. The region should be in between the two curves. I'm not considering any of the axes here. I'm just looking at the two curves. What is the region included between the two curves and also in from 0 to 4? This is one part of the region, and this is the other part of the region. Now I consider this as a bounded region. Why? Because I'm telling you that it is included only on this interval from 0 to 4. So I consider it as an acceptable region for me. He limited the consideration of the region in the interval from 0 to 4. I didn't take this, for example. Why? Because it is not bounded between both curves. I'm just looking at this one and this one. So I'm looking at this region. This is an open area. I don't look at the axes for you. So this is an open area for me. Okay, it is open in this direction. But this one is a closed area between the two curves, and as if there is a new bound on x equals 4. Okay, so now these are the two areas. Now do I need here how many strips would I need here? One strip or two strips? Two strips. Why? The first strip is this one. The second strip is this one. Both strips have the limits of the two curves, but we interchanged the limits. So if I call this curve 1 and this is 2, that curve would be 2 and that curve would be 1. When I interchanged the limits of the strip, it is considered as a new strip. Okay, so when I find the area for this problem, it will be broken into two integrals. The first integral is from 0 to 3, which was the same as the last problem for this one. So it will be 4x minus x squared minus x squared minus 2x dx. That was the above curve minus the lower curve. That was y equals to 4x minus x squared, and that was y is equal to x squared minus 2x. Plus, now we take it from 3, which is this point, the point of the circle, from 3 to 4. But now what is the above curve? It is the curve 2, which is x squared minus 2x minus the lower curve, which is 4x minus x squared. So this is the integral for this area. Okay, had we grasped the difference between the case that he given me an interval and for the case that he didn't give me any interval. If he didn't give me any interval, I would consider only the closed regions. But when he gave me an interval, a limiting interval, I considered the bound of the interval as new boundaries for the problem. So I may have some new bounded regions. some new closed regions. Okay, so that's for today's lecture.